Uh, in the last module, we discussed the layered view of computer design as well as the overview of computer architecture course. So, in this module, we look at the quantitative principles of computer design. So, before discussing the principles of computer design, let us spend a few minutes on looking at the growth in processor performance in the last 4 decades. So, this graph shows the growth in processor performance starting from 1978 all the way up to 2010. And the x-axis shows the timeline and the y-axis is the performance with respect to VAX 11780 emission. If you see the graph, the processor performance is increased almost like 25,000 times. So, the main reason for this high performance improvement in processors is because of 2 reasons. One is advancements in IC technology, the second one is advancements in computer design, which is mainly contributed by architectural innovations. So, if you see the graph, we can find 3 regions. One is from 1978 to 1986. In this period, the processor performance was almost 25% per year improvement. The second phase is 86 to 2003, where the processor performance increased significantly at a rate of 52% per year. And the last phase, the performance was not so much improved as that of the previous periods, but there is some improvement like 22% per year. And coming to architectural innovations in this first phase of the processor performance, it is mainly because of increase in the processor word size. So, started with a 4-bit processor to an 8-bit processor and so on. So, once you increase the processor word size, you can perform operations much faster. And the second phase of the processor improvement is mainly because of architectural innovations, which are typically exploiting instruction level parallelism, which is in other words like executing instructions, independent instructions in an out of order fashion, also implemented in superscalar processors, and also exploiting threading, so multi-threading, hyper-threading, simultaneous multi-threading and so on. And because of these things, coupled with multi-levels of cache hierarchy, we were getting a significant improvement in the processor performance. But in 2003, because of so many roadblocks such as the power wall, frequency wall, the thermal, because of all these reasons, the processor performance was not significantly improved. Note that if you see the second phase of this graph, we increased clock frequency starting from 22 megahertz all the way up to 3.2 gigahertz. So, this is effectively like a 1,000-fold increase in the clock frequency, which actually contributed to a significant processor performance. But the same trend we were not able to continue beyond 2003 because of the thermal issues. Remember that because of the advancements in the fabrication technology and the process technology, we are able to integrate more and more transistors on a single chip. According to Moore's law, the number of transistors integrated in a chip doubles every 18 to 24 months. And he gave this idea almost like 50 years back, and recently they have celebrated 50 years of Moore's law. Even today, the rule holds true. So, now imagine a scenario where you have billions of transistors on a single chip, and all these transistors are working simultaneously, and if you clock these transistors at 3.2 gigahertz or more, then they are going to consume too much power, and power per unit area is also called as power density increases significantly. And because of this power density translates to heat dissipation, and we will get the thermal issues. And because of all these problems, the technologists have decided not to increase the clock frequency at a rapid rate as whatever they were doing for the last 20 years or so. They said, like, rather than going for an increasing clock frequency, let us go for reducing the clock frequency or keeping the clock frequency at the same time, at the same point, but have more collection of processors. Each is a simple core and working together to compute a given problem efficiently. That is where the multi-core era started. So once you have a multi-core processor, rather than a one complex processor to do a given task, now we can have 2 or 4 small processors working together, and if the application is parallelizable efficiently, then we can improve the performance. That was the main design paradigm change in 2003, and using this multi-core scenario, we were getting a performance improvement of almost 20% per year after 2003. Now, of course, we are currently in multi-core era. Even if you see a mobile cell phone, we have like 2-core, 4-core, 8-core processors. So now we are in the multi-core era where the mantra is have collection of simple cores working together to solve a bigger problem efficiently. So effectively now, if you see the summary of this graph, it shows that the innovations in computer architecture play a key role in improving the overall processor performance or the system performance. Having said that, now we look at the principles of computer design. In the last module, we discussed that a computer architecture is nothing but instructions architecture, microarchitecture, and efficient implementation. So here we need to understand a point. Given an ISA, we can come up with multiple microarchitectures. For example, Intel Xeon processor and AMD Optron processor uses the same ISA, 64-bit x86 ISA. So that says that based on the application requirements, we come up with the functional requirements and we fix our ISA. But after fixing the ISA, we need to come up with an efficient microarchitecture, because there are multiple microarchitectures you can realize for a given ISA. And now the second point is, once a microarchitecture is fixed, it can be implemented differently. An example is a Xeon 7560 and Core i7 processors from Intel. Both have almost the same microarchitecture, but their implementations are different. When I say implementations are different, so they may clock at different frequencies and they may have different memory systems and so on. So from this 2 points, it says that the computer architecture is nothing but the design space exploration, because each microarchitecture, each implementation will have a different power performance points. So you have a spectrum of design points and you need to select a good design point based on your application requirements. So now, if you come up with an efficient computer architecture, which in turn provides us an efficient computer. So how do we come up with an efficient computer architecture? What are the principles we need to follow? The first point is, take the advantage of parallelism. If you see the computer, or if you say the computer design, we can exploit the parallelism at various granularities. Starting from a finer granular point, which is a bit level parallelization, all the way up to very coarse grain parallelism, which is the thread level parallelism. If you recall the graph, whatever we have shown in the previous file, the architectural innovations constitutes all these things. In the initial phase of the processor performance graph, we saw that it's mainly because of bit level parallelization. From the architectural point of view, we were getting the improvement, and when we come to the extreme end, the architectural innovations are mainly because of the core level parallelization or thread level parallelization. So when I say bit level parallelization, rather than performing operations on, let us say, 4 bits, if we perform operations parallelly on 8 bits, we can get more performance improvement. So effectively now, what is going to happen is, when I consider an 8-bit processor, if I want to perform 16-bit number addition, I need to read 2 instructions, one for LSB 8 bits and the other for MSB 8 bits. On the other hand, if I consider a 16-bit processor, I can do that in using one instruction. So the second point is instruction level parallelism, because most of the applications, if you see, the instructions can be independent in some scenarios, or even if they are dependent, we can overlap their operations. Execution of the instruction can be overlapped. For example, if you see the lifetime of an execution of an instruction, the instruction will follow through different stages. First is a fetch, second is a decode, third one is execute, memory read, memory write, and finally the commit. So if you see here, when an instruction is in the decode stage, the next instruction can be in the fetch stage. Similarly, when the first instruction goes to data read, the second instruction will go to decode, and the third instruction will go to fetch stage, and so on. So effectively, we can overlap the execution of instructions. This is called as a pipelining concept. We can exploit pipelining concept to improve the processor performance. And this is especially true when the instructions in some sense are dependent and so on. But if the instructions are completely independent and so on, and if the processor supports multiple functional units and so on, we can actually execute these instructions independently, and that is what the superscalar processors are going to do. We are going to discuss this pipelining and superscalar concepts when we come to the corresponding modules. But the instruction level parallelism is one of the main contributors for a significant growth of processor performance. After this instruction level parallelism, the next level of parallelism we can exploit is at the data level. For example, if you consider a graphic application, we may not always need operations to be performed on a 32-bit data, and most of the times it may be on byte level data, 8-bit data, and so on. You can perform operations, a single operation, on multiple data items. In other words, operations can be performed on a data stream. This is an example of SIMD, single instruction multiple data stream. Whatever we discussed in the last module, the Flint's classification of computer architecture, SIMD is one of the classifications. So SIMD architectures typically exploit the data level parallelization, and SISD exploits the instruction level parallelism. And after this data level parallelization, the next component is the thread level parallelization. Here, if an application can be divided into multiple tasks or threads, and if you have an hardware support to run these threads simultaneously, we can improve the performance at a rapid pace. So all these independent threads can be executed on multiple cores, and they will give you a significant improvement by reducing the overall computation time of that application. So effectively now, in order to exploit these different types of parallelizations, starting from bit level all the way to the thread level, we need to have a support from the microarchitecture, the hardware, the ISA. In other words, the architecture need to be supporting all these things to exploit these parallelizations. The next component is principle of locality. What is principle of locality? Typically, there is a thumb rule which says that a program spends 90% of its execution time in only 10% of the code. This says that the data and instructions that we used recently will be required mostly in the near future. So, there are two types of principle of locality. One is the spatial locality, the other one is temporal locality. What is spatial locality? Spatial locality indicates that if I access some data or instructions now, there is a high chance that I will access the nearby data and instructions to that particular recently accessed element. And the temporal locality indicates that if I access an item now, there is a high chance that the same item will be accessed in the near future. So, how can we exploit this principle of locality? For that, our microarchitecture needs to have the cache memory. We know that the data and instructions typically stored in the memory. Now, always going to the memory to access these instructions and data will be very costly, because the processor frequency is much higher compared to the clock rate with which the memory is operating. So, as a result, if you are always going to the memory, we are going to degrade the performance significantly. So, as a result, what we can do is, whenever we go to the memory, we bring a large chunk of data from the memory and put that in a fast memory, which is called as a cache memory, designed using SRAM based technology. When I say large chunk of data, it will not be in kilobytes or whatever, but typically we consider 32 bytes or 64 bytes of data. Anyway, we are going to discuss the cache memory in detail in the next unit. So, effectively we need to have the architecture that should exploit parallelism available at various granularities, and also we need to have computer architecture which need to support the cache memory. And the third and the most important component for improving the performance or to come up with an efficient computer design is focusing on the common case. For example, consider a scenario where you have a pipeline processor where different stages of pipelines are fetch, decode, memory read, execute and commit, and you also have set of functional units, adders, integer multipliers, floating point multipliers and so on. But if we see a scenario for executing most of the applications, we frequently access or use our fetch unit, decode unit, execute unit and so on, as compared to using the floating point multiplier. Given this scenario, we always have to put our efforts in optimizing this fetch unit, decode unit, execute unit and so on, rather than putting our efforts on optimizing a floating point multiplier. How do I quantify that if I optimize a particular component, how much performance I can get? Because we need to have some quantification mechanism so that before actually designing the processor, we will validate different alternatives and then come up with the best one. So, to do that, we consider the famous Amdahl's law. Before describing what is Amdahl's law, let us just define a speedup. Speedup is the ratio of the performance of an entire task using an enhancement applied when possible by the performance of the entire task without using an enhancement. Let us say we have an enhancement that we want to apply on a piece of code. When I apply, what is the performance I am going to get, and without applying that, what is the performance I am going to get. When I take the ratio of this, then I am going to get a speed up that shows that we will get this much speed up when I apply this particular enhancement on the piece of code. Now, having defined the speed up, let us look at the Amdahl's law. Amdahl's law says that the performance improvement to be gained from using some enhancement is limited by the fraction of the time the enhancement can be used. So remember, it has two components. One is the performance improvement to be gained by using some enhancement. The second one is the fraction of time the enhancement can be applied. So if the fraction of time the enhancement applied is 0, then you are not going to gain any performance improvement. On the other hand, for the complete execution of the time, if the enhancement is applied, then you will get a significant improvement in the performance. So by the way, the performance is inversely proportional to the execution time. So as a result, the speedup can also be written as the ratio of execution time for the entire task without using any enhancement by the execution time for the entire task when using the enhancement when possible. So this Amdahl's law can be expressed as the speedup achieved because of the enhancement applied and the fraction of time the enhancement is possible, which is nothing but it's 1 by 1 minus fraction of the time the enhancement is applied plus fraction of time enhancement applied by the speedup achieved because of the enhancement. We know that speedup enhanced is calculated by this particular formula. So this shows that even when you apply an enhancement, your overall performance is actually dictated by the fraction of the time the enhancement is considered. So let us consider a few examples to understand this Amdahl's law and then comparing design alternatives for different processes. The first example is, consider two processes A old and A new, and A old spends 30% of the time in computation and 70% of the time waiting for I/O operations. Some enhancements are incorporated in a new processor so that it achieves 15 times improvement in the computation time. What is the overall speedup gained by incorporating the enhancement? To know whether A new is better or A old is better, so we need to find the performance achieved with A new and A old. For that, we use the Amdahl's law, whatever we discussed in the previous slide. According to Amdahl's law, speedup overall is 1 by 1 minus fraction of enhanced plus fraction enhanced by speedup enhanced. This is effectively like, you can say, it's 1 by the fraction of component where enhancement is not applied plus fraction of time where the enhancement is considered by the speedup achieved because of the enhancement. And from the data given in the problem statement, the fraction of enhanced is 0.3 because 30% of the computation and 70% time is spent for the I/O, and we are applying the enhancement only for the computation part. So effectively our enhancement applied to 0.3% of your total execution time and 0.7% of the time where no enhancements are applied, and when I apply the enhancement, we know that the speedup we achieve is 15x. Substituting these values, so we will get a speedup overall is 1.389. This effectively says that a new processor will be having 1.389 times speedup with respect to A old. So effectively we can go for this enhancement and improve the performance. Consider a second example. When application where floating point instructions are responsible for 50% of the execution time for an application, while floating point square root is responsible for 20% of the execution time. And compare the following design alternatives, assuming that both alternatives require the same effort. Design 1 is make all floating point operations in the processor run faster by 1.6 times. The design 2 is speed up floating point square root operation by 10x speed up. So if we just, without computing, if we just look at this design 1 and design 2, and we may be tempted to say that floating point square root operation will be better because it gives a 10x speed up versus 1.6 speed up for the design 1. Now let us see whether that is true or false. According to again Amdahl's law, the speed up overall is equal to 1 by fraction of time where enhancement are not applied plus fraction of time enhancement applied by the speed up achieved with the enhancement. For the design 1, where we make all floating point operations execute much faster by 1.6 times, and we know that floating point operations constitute 50% of the execution time. So effectively 1 by 1 minus 0.5 plus 0.5 by 1.6 is equal to 1.23. Overall speed up we achieve with the design 1 is 1.23 with respect to the base processor. And design 2, we know that floating point square root operations constitutes 20% of the execution time. So effectively 0.8% of the time no enhancement applied, and 0.2 times we get an improvement of 10x in executing the floating point square root operations. So when we substitute these values in the Amdahl's law, we get the speed up of 1.22. So this shows that design 1 is better than design 2. Remember, in these two examples, we consider the optimizations incorporated within a processor, but actually Amdahl's law can be applied across processors also. To illustrate that, let us consider a simple example. When parallelizing an application, the ideal speed up achieved is equal to the number of processors. What is the speed up with 100 processors if 80% of the application is parallelizable, ignoring the cost of communication? Let us consider an ideal scenario where communication cost is 0. And in the ideal setup, if I have n processors and if my code is thoroughly parallelizable, I can get a speed up of n. So now in this particular example, we consider 100 processors. Now we will see what is the improvement we will get with these 100 processors when my code is 80% of parallelizable. So we can restate Amdahl's law as speed up overall is equal to 1 by 1 minus fraction of time parallelizable plus fraction of time parallelizable by speed up achieved with the parallelization. It is nothing but 1 by sequential portion of the code plus parallel portion of the code divided by the speed up achieved with the number of processors. Note that when the code is sequential, even when you have 1000 processors, you have to execute the sequence of instructions in the sequential portion in a serial fashion. So you won't get any speed up. But whereas if the portion of the code is parallelizable, and when we assume that the communication cost is 0, and in an ideal scenario where every instruction is executed, it takes 1 unit of time and so on, so we can get with the 100 process we can get 100x speed up. So substituting these values in this equation, so fraction of parallel portion is 0.8, sequential portion is 0.2, and effectively the speed up with 100 processors is T1 by T1 by 100. Well, T1 is the total time it takes for a single processor to complete the task, and the speed up is 100 here, and the speed up overall is 4.8, which shows that even when you have 80% of the code parallelizable, and even with 100 processors at your disposal, you can get not more than 5% improvement in performance. So this also shows that to have an efficient computer design, in addition to having an efficient computer architecture, we need to have support from the different other layers of the computer design. Those are like algorithmic layer, high level programming layer, the operating system layer, the system software, everything. We need to have an efficient compiler, we need to have an efficient program, we need to write a parallel program. So all these things actually contribute to the overall efficient design of a computer. We will use a processor performance equation. We define a CPU time is nothing but the total number of CPU clock cycles an application takes when we are executing that application on a given processor. Remember, if I just give you CPU clock cycles without considering the cycle time, it makes no sense, because I may say 100 CPU cycles on one processor versus 1000 CPU cycles on another processor, and if the first processor is running at 10 megahertz frequency and the second one is working with 1 gigahertz frequency, so which one is better? Actually the second one is better, even though the number of clock cycles it takes is more. The reason is the second processor is working at 1 gigahertz frequency, whereas the first one is working at 10 megahertz. So in other words, when we specify the clock cycles, we need to give the cycle time also. Effectively, the total CPU time for an application to execute on a given processor is equal to the product of the number of CPU cycles and the CPU cycle time or the clock cycle time. So once we consider the CPU's time, we also can measure the number of instructions in a given program, that is denoted as instruction count or IC. Once we have an instruction count and also the total number of CPU clock cycles for a program, we can define clock cycles per instruction or CPI. CPI is the ratio of CPU clock cycles for a program and instruction count. So when we substitute this in the first equation, so your CPU time is equal to instruction count times clock cycles per instruction times the cycle time. So effectively, given a program and also given the characteristics of a processor, we can identify what is the clock cycle time, we can identify what are the number of instructions in the program based on our ISA, and we can calculate the CPI when we execute the program on the processor. So to optimize the CPU time, because ultimately our overall idea is to improve the overall performance. To improve the performance, you need to reduce the execution time. In other words, we need to reduce the CPU time. To reduce the CPU time, either we can optimize instruction count, or we can optimize CPI, or we can optimize the clock cycle time. But this is not that straightforward. If you try to optimize one of these things, it has an impact on the other two components. The reason is, IC instruction count is actually dependent on the given ISA and the compiler technology. So we can come up with a complex instruction to perform a complex task versus a simple set of instructions which may require 4 instructions to perform the task. Now in the complex instruction scenario, my IC is equal to 1. In the simple instruction scenario, my IC is equal to 4. So if I go for the complex instruction, then IC is equal to 1, but the problem with that is, because the complex instruction is considered, it is going to increase your clock cycles per instruction. So effectively, when I am trying to optimize one component, it has an impact on the other component. Clock cycle time depends on the hardware technology and the microarchitecture. So this effectively shows that each of these components are determined by multiple different the components. So we have to be intelligently optimize these things without having a significant impact on the other components. Then only we can improve the overall performance of the system. So we know that CPU time is equal to the product of IC, CPI and clock cycle time. This can also be written as the sum of the products of instruction count of a particular type of instruction and its cycles per instruction times cycle time. For example, I have an application which consists of add instructions and multiply instructions. 80% of the instructions are add instructions and 20% of the instructions are multiply instructions. Now if I want to compute the CPU time for that particular application, all I have to do is, so 0.8 into CPI of add instruction plus 0.2 into CPI of multiply instructions, take this sum and multiply with the cycle time. This can be written as ICI by IC, where ICI is instruction count of a particular instruction type by the total number of instructions in the program. It's effectively like take the fraction of the instruction type, multiply with the corresponding CPI and take the sum of all in the program and then multiply with cycle time, you will get the overall CPU time. Let us consider an example. Consider an application where the frequency of floating point operations is 25% and the average CPI for the floating point operations is 4. The average CPI of all other operations is 1.5. And assume that the frequency of floating point square root operations is 2% and the CPI of floating point square root operations is 20. Now whether decreasing the CPI of floating point square root operations to 2 is better as compared to decreasing the average CPI of all floating point operations to 2.5. So how do we compare these two design alternatives and suggest the best one? To do that, we use the processor performance equation. We know that CPI original is equal to the sum of the instruction count fraction times its corresponding CPI. So in the original case, we have 25% of the instructions are floating point, which takes 4 cycles as CPI, plus the rest of the instructions are 75%, which takes 1.5 as CPI. Is effectively 2.125. And CPI of design 1, in the design 1 we say that we can go for optimizing floating point square root operations so that it reduces the CPI from 20 to 2. So the CPI of design 1 is equal to 1.765. Yes, this is better than the original CPI, but it is not saying anything about whether it is better with respect to design 2. Let us see what is the CPI of design 2. So the design 2 is we optimize all floating point operations and the average CPI of all floating point operations now reduced to 2.5 as compared to the original 4, and we have not touched any of the other non-floating point operations which have CPI of 1.5. So it is the total CPI for the design 2 is 1.75. So which says that the design 2 is better than design 1. Remember, when we say design 2 is better, because its CPI is reduced. Because lower the CPI, we are going to get higher performance, because we spend minimum number of cycles to execute an instruction. So lower is better when we consider CPI as a metric. So effectively design 2 is better, in other words optimize all floating point operations rather than considering floating point square root operations. This also again come back to our previous discussion concentrate on the common case, because floating point operations constitute 25% of the total operations, whereas the floating point square root contributes only 2% of the total instructions. So with this, I am concluding this module. We are going to discuss the instruction set architectures. Thank you.